Hello everyone. So welcome back to the latest lecture session. So in the last couple of sessions we have been looking at, I guess, a couple of examples, right, that would help you understand, let's say, where the course content would be relevant, or how the aspects that you are going to learn during this particular course are going to fit in with respect to the relevant applications, let's say, right. I think we looked at one particular example in Ghaziabad, right, where I think the groundwater was contaminated by chromium, right, and we looked at how they were pumping the water out and then treating it and so on. And I believe then we looked at another example where we had relatively more data, right, available in the public domain, and then we looked at the relevant aspects. I think we looked at, if I am not wrong, risk assessment as in site characterization, data collection, and what is risk assessment, certainly, I guess, right, and then coming up with relevant remedial alternatives, as in that obviously, as I mentioned earlier, is going to be what we are going to talk about in great detail or technical detail, right, but we haven't discussed that in great detail obviously during that particular example, I guess, right. And then we looked at how, let's say, different aspects come into play when choosing one of these alternatives as the one that needs to be followed through, I guess, right. So then I guess we started looking at the course outline in greater detail. So today we are going to wrap up looking at that particular course outline, as in I am going to give you a brief overview of each of these aspects that we are going to discuss during this particular course, right, and then we are going to move on to the relevant aspects, right. So coming back to the course outline here, as mentioned yesterday, we are going to look at some of the laws here that are going to be relevant in the Indian context. So with respect to the laws and regulations, let's say, we are going to look at that briefly, maybe today itself, and then move on to risk assessment, right, risk assessment, and then come back to laws and regulations, I guess, right, in greater detail. So again, as we talked about in risk assessment, right, we usually have two kinds of risk assessment. They are human health risk assessment and ecological or environmental risk assessment. Typically what we usually look at is human health risk assessment, and as I mentioned earlier, the ecological risk assessment is much more time and resource intensive, I guess, right, and also obviously depending upon the what do we say, type of contamination or extent of contamination and the relevant remediation required, we are going to either go for or not go for ecological risk assessment, right. But certainly we are going to look at the human health risk assessment. In that particular aspect, we usually have four major aspects to consider. Obviously data collection and evaluation, right, and we are going to discuss this in detail, and then exposure assessment, toxicity assessment, and then risk assessment, I guess, right, and then risk assessment. And all these four aspects come into play when one looks at risk characterization, right, and more or less we look at the holistic picture, and then obviously risk management, as in what aspects need to be looked at or followed through to be able to, let's say, bring down the risk to acceptable levels. What are the relevant aspects required, and communicating the risk with respect to not with respect to, pardon me, to either the public or the relevant authorities out there, right. Again, these are the different aspects out there, so we are going to discuss this in great detail. So then we will move on to the next major aspects, which would be, I believe, we are going to look at, let's say, groundwater or contaminated groundwater, and we are also going to look at contaminated sediments or soil, right. So this particular aspect would make up, let's say, a major chunk of our particular course, this as in remediating contaminated groundwater, right. The second major chunk would be with respect to looking at the relevant aspects about remediating contaminated sediments or soil. So in this particular aspect, we have obviously, let's say, plume containment, right, wherein we dig extraction wells, injection and extraction wells, or just barriers. As the name indicates here, it's containment, right, it's plume containment. So here we are not trying to treat the what do we say, contaminant or such, we are only trying to contain the plume so that we avoid, let's say, the spread of the contaminant over a much larger area, and thus affecting or potentially affecting larger populace, right. So that's the particular aspect here. We are going to look at the relevant aspects, the types of materials, the hydraulic conductivities here that we are need to look at, right, and these aspects out here. So moving on though, we are going to look at pump and treat next, again with respect to or in the context of remediation of groundwater or contaminated groundwater. So obviously we looked at one example out there in Ghaziabad, right, where they were pumping out the particular chromium contaminated groundwater, right. So obviously again we are going to look at the relevant aspects, as in where do I need to place the pump, right, as in if this is the plan view and this is my contaminated plume, this is the plan view, right, and this is the source of contamination and groundwater flow is in this direction, and let us say after certain time this is the boundary of the contaminated groundwater at a particular concentration, let us say, okay. And now I need to be able to pump out this particular water. Obviously if I have the pump out here and the groundwater flow being in this particular direction, right, will it be able to capture the entire, what do we say, plume? Probably not, right, not probably, not really, right. So here we are going to have to be able to come up with a scientific explanation, or scientifically what do we say, an explanation based on science, let us say, right, that would help us what do we say, try to capture the plume here, right. So in that context we are going to look at the number of wells in the first case that are required, right, the distance between the wells required, and then the distance between the top edge of the plume and the center line of the wells, right, and then we are going to look at, let us say, the capture of the plume here, right, based on the capture lines or flow lines here, right. So these are the aspects we are going to look at, and in general we are going to look at the Havendel et al. Design, right. Based on those aspects we are going to come up with that. Obviously the relevant aspects such as the maximum allowable drawdown and such, we are going to consider that, confined, unconfined aquifer and so on. So those aspects we are going to look at that, and once obviously we look at that particular what do we say, aspect, we are going to have to move on to understand, let us say, in which cases is this going to be relevant or feasible, and in which cases will this not be feasible. So in that context an example would be, let us say, here we are pumping out the groundwater, right. So obviously a compound that is hydrophilic or would want to stay in the aqueous phase, right, would be our pump and treat would be better in such cases. But if the compound is hydrophobic, let us say it's a chlorinated solvent, let us say, or chlorinated organic, pardon me, right, or a hydrocarbon, let us say, right, as in you have these petrol and diesel stored in underground storage tanks beneath your petrol bunks, right. Typically they are great sources of pollution, but maybe are not of great concern as of now in India, because I guess people have other priorities, right, or other pressing or more important priorities, let us say. But again, that is of great concern worldwide, and certainly in India too, I guess. Right now probably we are unable to spare time or money to look at these aspects. Again, coming back to what we were discussing, so let us say we have what do we say, leak of this underground storage tank, right. So let us say we have this underground storage tank, and this is the petrol bunk out here, let us say, right. Please excuse my poor drawing skills, I guess. Let us say this is my underground storage tank. So typically they develop leaks, and then let us say you are going to have leak of your particular hydrocarbon. So as we know, let us say the hydrocarbons and again chlorinated organics in the case of industrial solvents are hydrophobic, right. So if you look at the equilibrium between the organic phase and, let us say, organic phase as in the organic fraction in the soil and the groundwater or the aqueous phase, where would the compound want to, what do we say, stay, let us say, I should not use the term stay, let us say, where would the concentration be relatively higher? The concentration would be relatively higher, or the compound would be would prefer to be adsorbed onto the organic fraction in the soil rather than be present in the groundwater. So thus if you are just trying to use pump and treat in this particular scenario, as in, let us say, if I have soil out here and my hydrocarbons adsorbed onto this particular soil particle, and this is the water surrounding it, and let us say the number of moles on the particular in the groundwater are relatively less. So if I keep trying to pump out this particular groundwater, right, so there are going to be considerable issues that are going to come into play, as in, let us say you are going to have tailing and rebound, right, and again the time required for your particular pumping, pumping out the relevant contaminant in this context, because there is going to be desorption from the soil, as in because the compound is adsorbed onto the soil, preferentially adsorbed. So as you pump water out, right, and let us say water at relatively less concentrated or water with less concentration of this contaminant comes in contact with the soil, again you are going to have desorption, right. But again this takes time, and the soil acts as a reservoir of contaminants. So these aspects need to be considered, obviously, right. So again those aspects in pump and treat. And then source control, let's say, how can we, let's say, if let's say you are able to detect the spill, let's say, within a limited or a relatively little period of time, let's say, right. So then let's say you can look at options to control it at the source itself, rather than let it what do we say, it as in the contaminant contaminate a wider what do we say, pool of groundwater, right. So then we can move on to permeable reactive barriers. So again the name is relatively self-explanatory. It's permeable reactive barrier, right. So let's just look at a quick example here, let's say. So and some of the advantages in this context, let's say. So here let's say the soil surface, and let's say this is the groundwater surface, right, groundwater level, pardon me, right. And let's say this is the side view, obviously this is the side view. Let's say there has been a spill here, and it has reached the groundwater, and the plume is spreading in this direction, let's say, right. So different options out there, but obviously again people try to look at cost and convenience, right, and obviously effectiveness to go along with that. So obviously passive techniques such as permeable reactive barriers are relevant here. So how do I go about that? I am going to build a permeable reactive barrier. So it is going to be relatively porous, obviously. Why porous? Because you would want the groundwater or the contaminated plume to flow through the barrier and not around the barrier. For example, if the porosity of the barrier is, let's say, lesser than the porosity of what do we say, or if the hydraulic conductivity of the barrier is less than the hydraulic conductivity of the surrounding aquifer, the plume would obviously want to flow around it, right, rather than through this particular barrier. Again, path of least resistance, if I may say so, right. So again, I am going to design the barrier in such a way that obviously the plume would prefer to flow through that. And for this, what do I need? I need to know the shape of the plume, extent of or the distribution of the plume, and so on. And more importantly, I need to know what are the contaminants present in this particular plume, right. So if it's an oxidized contaminant, I am going to have a reactive barrier made of reducing or reductant or reducing agents, I guess, right. So as the groundwater or contaminated groundwater passes through the barrier and then leaves the barrier, right, the kinetics and such, right, if this is C versus T, right, if this is C versus T, right, as it passes, not T, let us say thickness of the barrier, if I can say so, or length, it is going to be a what do we say now, a plug flow reactor, obviously, right. So again the concentration is going to decrease as the contaminant moves through the barrier, right. So again there are obvious advantages here, as in you do not need continuous what do we say, operation and maintenance here. You do need some monitoring wells, and obviously being subsurface, let's say obviously depending on different kinds of techniques, the amount of area required, let's say, is going to be less. And this is relevant in the Indian context. Why? Because obviously the cost of land is pretty high. I mean, the demands on the land are pretty high, and thus the land costs are pretty high, and in that context the PRBs are a pretty good option. But obviously depends upon site conditions, is it feasible or not, what is the depth of the particular plume and such, right. Again, we are going to go in detail with respect to the PRBs later on. Moving on, so again one major aspect, as in natural attenuation or monitored natural attenuation. I guess this is more widely used out there abroad too, right, or in the Western world, but certainly has relevance in the Indian context too. Why? Again, we have microbes out there that like us, they want to thrive too, right, and so they look for different sources of energy. So if the conditions suit them, as in you have what now, an electron acceptor and an electron donor, let's say, right, and if you can create the relevant conditions for the either the cell to microbes or for the native population, let's say, right, a native population of microbes, you can have natural attenuation of the relevant contaminant. Again, when we talk about natural attenuation, rather than just degradation by microbes, we also talk about, let's say, or need to take into account effects of dilution, as the groundwater or as the contaminant is dispersed, let's say, right. We are going to look at effects of dilution there, and again obviously advection too, right. So again different aspects, and we need to look at these particular aspects in greater detail. Usually natural attenuation in conjunction with other treatment what do we say, techniques is looked at. For example, let's say I have this is the side view again, this is the groundwater level, and let's say this is my contaminant here, right, and let's say the contaminant is plume is out here, right, and if I draw the particular graph here as in concentration and with distance starting from here, distance. So, what do I see? Let us say initially the concentration is very high, let us say maybe way too high such that it is toxic for the microbes too. So, what can I do? Let us say I can construct, let us say maybe a PRB here, right. So, let us say if I construct a permeable reactive barrier here and design it in such a way that at the end of this particular, I guess it is not to scale, pardon me. So, let us say by the time it reaches the PRB, then it is going to be a considerable drop, and then let us say I can let the microbes do the job. As in here we have the extraction wells where people are drawing the groundwater from, right. And so, by the time it reaches this particular point, let us say we are going to design it in such a way in conjunction with both the PRB and natural attenuation, let us say, such that by the time it reaches the receptor well, let us say, or the receptor, let us say, the concentration would hopefully be, not hopefully be, would be within the what do we say, threshold levels or the relevant regulatory levels, I guess, right. So, again natural attenuation, different aspects obviously, and one major aspect though is that monitoring is a key aspect here, right, as in you need to be able to establish a wide network of what do we say, monitoring wells, let us say, to understand that your underlying assumptions are, what do we say, valid over time too, right. Again moving on. So, again as we talked about, we have looked at various options typically looked at when remediating contaminated groundwater. So, the next major chunk would be with respect to soils and sediments, I guess, right. So, you have contaminated soil, let us say, and how do I go about it now? As in it might be the case that groundwater has been contaminated or probably not had been contaminated, and it is just the soil that is contaminated. What are the aspects out there? So, obviously the one that most people in India look at, let us say, is excavation, I guess, right. So, they try to excavate the soil and then dispose it in a hazardous waste landfill, right. So, but what are the issues here? The cost, I mean if the extent of contamination is relatively high, or the area is relatively huge, let us say, what is the issue here? Obviously the costs, I guess, right. And we are going to do some what do we say, math here in that context, as in just look at some of the values out there that take into account the cost of hiring, let us say the relevant transport, and also cost for fuel and transportation and so on, and see that depending upon, what do we say, the location of the TSDFs or the hazardous waste landfills in our country, is typically not feasible if we look at certain areas or volumes of soil, I guess, right. So, again typically what do people do though, as in they excavate the soil and take it to the landfill and dump it there, but again that in my opinion is not what do we say, sustainable in the long term, especially in a country like India, as in we are not what do we say, degrading the contaminant, we are only removing the problem from one particular place to concentrating it in another relatively contained area, I guess, right. Again excavation, so again we are going to look at the relevant costs, and then with respect to landfill we are going to look at in relatively greater detail with respect to the two kinds of landfill that we have out there. So, one would be the TSDF or hazardous waste landfills. TSDF is the term given to the hazardous waste landfills in the Indian context, and obviously the solid waste or municipal solid waste landfill, and we are going to give greater emphasis to the designs required with respect to the hazardous waste landfill. Typically you need two impermeable HDPE membranes, as in you want to what do we say, arrest the leachate reaching the groundwater, as in let us say a very generic figure here please, if this is my landfill, let us say, and obviously there are going to be different cases with respect to the cover. So, here again what do we need? I guess we are going to have two HDPE membranes here, let us say, and obviously leachate collection layer and clay layer and so on, let us say, right, and such that the leachate that we generate, let us say, from the landfill does not reach the groundwater table or level here, right, does not reach the groundwater. We are going to capture it above the first impermeable layer, and if let us say over time some particular some amount of leachate reaches the second layer, we are going to have to try to capture that too. But I guess I came to know that CPCB has sometimes been insisting on three what do we say, layers of impermeable liners too. Again I think as an extra level of safety, I guess, right. Again different aspects here in this case, or different scientific or technical aspects, we are going to discuss them, I guess, right. And then again containment, let us say, as in let us say we have contaminated soil here, this is the soil surface and this is again the plan view, we have contaminated soil here, let us say, right. So let us say if there is rainfall, let us say, right, again you are going to have contaminated runoff, let us say, or you can have leachate again. So how do I contain this particular contaminated soil in situ, let us say, right, in situ or at the site. So I need to look at barriers. So what kind of barriers? Barriers can be synthetic barriers or can be made of bentonite clay too, right. Again bentonite clay, the hydraulic conductivity is remarkably less too, right. So again different aspects in that context. And then we are going to look at what do we say, solidification and stabilization, and we are going to spend, as you can see, considerable time in this context. So solidification stabilization, I guess, is self-explanatory, slightly self-explanatory anyway. So what is that about now? So you have soil, let us say, or let us say a slurry, let us say, that is contaminated now. So what do you need to do? You need to solidify that or improve the physical characteristics of that particular slurry or contaminated soil or sediments in the first case, right. And then you are going to stabilize that. What do you mean by stabilize? I am trying to immobilize the contaminant such that even if let us say water or acid comes in contact with this particular contaminant, right, it is not going to what do we say, leach into the or equilibrate into the acid or the water that comes in contact. So there are two aspects involved. One would be obviously improving the physical characteristics of that particular waste if required, and the second one would be to immobilize the relevant contaminant, right. And this I think is the second, not think, it is the second most widely used remediation technique for contaminated soils out there, especially in the western world, I guess, right. And certainly I believe it is catching up, or if it is not, it is time to catch up in the Indian context too. So in this context obviously we are going to look at two different models, single component and multi-component leaching models, right, and how that works. And in general in this context we are going to look at the design approach, as in one design would be to what do we say, pass the test or the TCLP test, right. TCLP test is the one that people use out there, or the regulations define that you need to look at the TCLP test to see if a particular waste is toxic or no. So anyway, we are going to look at that in greater detail, but anyway TCLP based approach is like you trying to prepare for an exam only to pass the exam, let us see. And then risk based approach is to looks at site specific scenarios and tries to what do we say, limit the what do we say, or increase the effectiveness of your remediation such that the actual risk at the site is minimized, let us say. And thus I guess the corollary is that you learn the material because you like to learn the material and not just for sake of passing the exam, which is similar to the TCLP based approach, I guess, right. So again moving on, and then obviously we have chemical treatment of the soil. Obviously let us say if depending upon site conditions, each of these techniques or remediation techniques that we have looked at until now have their own limitations and such, right. Again depending on the scenario though, if we can either have non-redox reactions or redox reactions, I guess. So oxidative process, in situ chemical oxidation, ISCO, in situ chemical oxidation, something that is widely used, let us say. And again obviously you are going to put an oxidizing agent, let us say depending upon porosity, maybe ozone, let us say, or permanganate and so on, let us say, right. And we are going to look at the relevant aspects involved here, right. And again we are going to look at surfactant extraction, let us say, right. As in let us say your compound, let us say, is hydrophobic, right, it does not want to stay in the water, it only wants to absorb onto the organic fraction in the soil, right. So how do I get that out here? So let us say similar to, let us say, maybe if you think there is a grease or oil on your particular hand, how do you get that off? You use soap to wash it out, or it's surfactant more or less, right. Or you can say we are going to look at micelle formation, partitioning of these particular contaminants from the organic fraction in the soil into the micelle. So earlier they were adsorbed onto the soil. So after adding the surfactant and forming the micelle, let us say, we are going to discuss what it is or they are later on, the contaminant is now going to change phase into the micelle. And then again because surface tension relatively less, we can pump this surfactant out and then treat it and so on, right. So that is something again that is widely used, again depending on the kind of scenario that you are facing, right. So again moving on, soil vapor extraction, again that is self-explanatory, right. Again depends on site conditions depending upon the porosity too, right, and interconnectivity of the pores. So soil vapor, I guess, right. So either I create vacuum conditions, let us say, as in this is the side view now, side view, and let us say this is my ground surface, and below the surface this is my contaminated soil, let us say, right. So what can I have now? Let's say I need to have injection wells for the air, let's say, or I can have extraction wells or vacuum wells here, right? Depending upon type of scenario, you can either inject or push air through or have vacuum wells and so on. And then let's say depending upon the pores and interconnectivity of the pores, let's say you are going to have or extract the soil vapor, I guess, right? Obviously, in which particular scenario would this work out or be feasible though? Obviously, when the contaminant is relatively volatile, as in let's say hydrocarbons. As you know, petrol and diesel, they are volatile, right? They would rather change phase into the gaseous phase rather than stay as a liquid or be adsorbed onto, let's say, soil, I guess, right? Certainly, they do not want to stay in what do we say, the aqueous form, right? Certainly, anyway. So in that context, let's say if your soil is contaminated with hydrocarbons, let's say, so depending upon, let's say, the temperature, let's say, you can look at soil vapor extraction to extract the relevant contaminated what do we say, or contaminants, I guess, right? And then treat the air again, obviously, yes. So that's one particular aspect here, and we are going to look at the relevant designs and such in this context. So again, moving on, similar to what do we say, groundwater remediation, obviously we have bioremediation and phytoremediation here. So again, people usually come up with phytoremediation or bioremediation as what do we say, cure for all kinds of contaminants, but that's not the case, right? In general, let's say if a compound is not being degraded at a particular site, there are certain what do we say, well, nature dictates most of what goes on, right? And let's say if a particular contaminant at a site is not being degraded over time, it means that the conditions at that particular site are not suitable for the propagation of the microbes that can degrade these contaminants now. So you can try to, let's say, introduce some species, let's say, or colonies of microbes that you isolated from some other place into this particular locality, which is a contaminated site. But then let's say it depends upon, let's say, different aspects, as in temperature, availability of electron acceptor and donor, and so on. Or let's say sometimes the native microbes can feed off these particular what do we say, substrate that is required for these engineered microbes or non-native species, right? As in, I'm introducing some species which are not native to that particular site, because I think, let's say, they can degrade the contaminant in a faster rate. But then let's say again, it's a rule of survival of the fittest, right? So in general though, again, engineered species haven't had a great deal of success, but maybe if you were able to isolate, let's say, species from conditions where the microbes have thrived under such stressful conditions and brought them in here, maybe yes, the chances are that it can work out. But there are other aspects that need to be considered, and we are going to look at those aspects, I guess, right? As in, what are the conditions required for propagating bioremediation, and also we are going to look at phytoremediation, let's say, and again look at the relevant aspects and maybe try to dispel some myths about it, I guess, right? Again, we'll move on. So week 12, I believe this is the last particular set of topics we are going to discuss in general. So one, obviously the thermal process in general, again slightly costly, obviously, because you have energy demands and such, but obviously when depending upon the site conditions and the extent of contamination, yes, that can be looked at. So incineration, obviously, right, last resort again, or if nothing else is feasible, obviously incineration, yes. And thermal desorption, right, you increase the temperature, right, again look at delta G values and such and change with temperature and such, right. You want to increase the desorption and thus thermal desorption. And then lastly, soil washing, as the name indicates, it is soil washing, as in you literally wash the soil, right, and we are going to look at that particular design. So, and I guess with this particular session, you should have an overview right now about what it is we are going to discuss in greater detail. Right. So, I guess I am going to end my session for today, and from next session I am going to start looking at the laws that are, or the law, let's say, that's relevant to the hazardous waste, right. I think it was promulgated in 2016 if I am not wrong. So, we are going to look at that briefly and then move on to the risk assessment related aspects, and then move on to, let's say, or come back to laws in greater detail, I guess, right. And I guess with that I am done for today, and thank you.